marked the history there. So, serving as a visiting scientist at the European Center for Research in Nuclear and Particle Physics in Geneva, Switzerland, from 1996 to 2015. In 1991, Professor Kaur was awarded the prestigious Giglio Fellowship at Paris, Italy, in recognition of her outstanding contribution to the field of physics. Currently, Professor Kaur serves as a principal investigator at ESP CMS Research Project at Punjab University. Additionally, she holds the esteemed position of Associate Scientist at CERN in CMS experiment, where she leads the PU group. I would also like to introduce Professor Ramandeep Johal, uh, who is very acquainted with myself also. Professor Ramandeep Johal is a distinguished academician and researcher currently serving as a professor at Indian Institute of Science Education and Research, Mohali. Commonly, it's called IISER-Mohali. In 2008, Professor Johal joined the faculty at IISER-Mohali, where he has since actively engaged in research and teaching. Professor Johal has obtained his PhD from Panjab University on quantum algebras in 1999. Eager to broaden his horizons, Professor Johal pursued a Humboldt postdoctoral fellowship at Technical University, Dresden in 2001, where he further honed his expertise. His scholarly pursuits have led to publication of over 80 articles in esteemed international journals, solidifying his reputation as a leading authority in his field. So, before Professor Jeev is going to introduce our other two panelists, uh, one of the very beautiful lecture that Professor P.K. Ahluwalia, gave at our institution, it was a mind-blowing lecture in which he just gave us a glimpse that why this quantum computing is going to take a central stage in this quantum in the education world as well as in the manufacturing industries also. So today we were dealing with the classical computers, which can have billions of logical operations per second. But Professor Ahluwalia just told us that the world is of the quantum computers, in which you can have a total control of molecular level simulations with the help of IBM is working on this, and they have came with the computers with strong foundation so that they can work on simulation at the molecular levels. So that will be a wonderful climate seismology that can also be governed through this quantum computing, because when the classical computers have failed to reach at that level, like the genome prediction and some other analysis of some virus, their quantum computing will be going to take a central stage. So, Professor Ji, please, you can introduce our two other panelists. Professor Ji, are you there, Professor Ji? Hareen sir, Professor Ji is there.
Yes, sir.
By that time, maybe there is a technical problem. Professor Ji, are you there? Anyway, let me introduce our distinguished panelist, Professor Madhurima. As Professor Ahluwalia has, gave us stern instruction that you should introduce first of all Professor Madhurima. So I'm just following that instruction. Professor Madhurima is a professor at Central University of Tamil Nadu. Professor Madhurima obtained her master's and PhD in physics from IIT Madras. Following her postdoctoral studies, Professor Madhurima embarked on a journey of teaching and research. She honed her skills as a postdoctoral fellowship at University of Hyderabad, where she worked under the and as a CSIR research associate. Her dedication and contributions to the field were recognized with JNSTS Award from the Development Government of Tamil Nadu. In pursuit of academic endeavors, Professor Madhurima moved to Mizoram University, where she served as a reader and later as an associate professor. Professor Madhurima joined Central University of Tamil Nadu in 2012, where she is currently a professor of physics. Professor Madhurima has a wide administrative experience, having served as a head of the department, chairperson of CASH GSCU, director of IQAC, member of academic and executive councils, and now a member of university court. In addition to teaching, research, and administration, Professor Madhurima has keen interest, gender equity, online teaching. Her commitment to excellence and social responsibility serves as inspiration to students and colleagues. So, with this brief introduction of Professor Madhurima, I would like to first of all say very high words about Professor Ahluwalia because, sir, I will called you in person also that the speakers that were available in last sessions, they were really a gem of India, and I requested Professor Ahluwalia also that, sir, this is a very big platform, you should make this IAPT as an international brand, so that was a great impetus to this IAPT. So let me introduce, he needs no introduction, but still I have to formally give his introduction. Professor P.K. Ahluwalia is President of Indian Association of Physics Teachers. Professor P.K. Ahluwalia is retired professor of physics from Himachal Pradesh University, boasts a distinguished career marked by significant contribution to teaching, research, and administration. With extensive research experience spanning over 4 decades, Professor Ahluwalia has held numerous prestigious positions, including Professor of Physics, Coordinator UGC, SAP, and membership in various advisory committees and councils. His expertise lies in condensed matter physics with notable research in areas such as dilute magnetic alloys, chemisorptions, and quantum dots. Professor Ahluwalia has published prolifically with over 120 research papers in high-impact journals and several authored books. Beyond academia, Professor Ahluwalia has been recognized for his outstanding contributions, receiving awards such as Commonwealth Academic Fellowship and Best Teacher and Academic Administrative Award. So this was the formal, outline of your, introduction. But I would like to say a few words informally that Professor Ahluwalia now is honing his research in, painting. Participants do follow the Instagram page PK Ahluwalia. You will search and you will see that how beautiful painting he is. He is diving in the ocean of, philosophy also in the quantum mechanics maybe. So, sir, I have personally seen your painting also when you were there, but definitely I would not bearfet other participants that they should also follow the things that you have doing, that a physicist is doing a lot of things in other areas also. So that's great. So this was a brief introduction. And now I request again Professor Jeev, if he is there, to start with our formal, questions to the Professor Jeev. Are you there? Dr. Helene? Dr. Helene? Professor Jeev is there or not? Professor Jeev? Anyway, sir, Ahluwalia sir, may I start with the questions for the panelists? Professor Ahluwalia?
Yeah, please start.
Right, sir. So, to start with, first of all, I would like to invite answers from Professor Manjit Kaur. So, ma'am, you have, worked in that, famous experiment. So, my first question to start the ball rolling is that how quantum study helps to unravel the mysteries of universe. That was a very famous experiment, and how to a common layman, if he can understand, he or she can understand how this unravel the mysteries of universe in a simple language. So, may I know, ma'am, Professor Manjeet?
उनको सुनाई नहीं दे रहा है एक्चुअली ना. Ma'am, please unmute yourself.
Professor Manjeet, Professor Manjeet, may I repeat the question, Professor Ahluwalia sir?
Actually, question is fine, but She is not able to receive something, it seems.
I think we were all made participants and we were unable to unmute. I think you have to make her a host.
Yes, I have allowed that. Now she can unmute herself.
Yes, now I can unmute.
Yeah.
Yes. Ma'am, have you heard that question?
Yeah, please, can you please repeat the question?
Ma'am, we are very already we have I've said that we are very proud that you were in the part of that famous experiment. And ma'am, how this quantum study helps to unravel the mysteries of universe and so that it can understand in a very simple and common man language or layman language.
Okay. So, can I first of all, I would like to convey my thanks to the organizers for inviting me as a panelist. Now, the second observation I would like to make here is the title of the workshop was very amazing. Alice in Quantum Land. So here, this Alice probably is the name which derived from one of the Disney World movies, Alice in Wonderland. I would like to rename this as Alice as an acronym. And this acronym stands for a Large Iron Collider Experiment. This is one of the experiments which is currently going on at CERN. One out of the 9 experiments which is happening, one of the very fascinating experiment at CERN in Geneva, Switzerland. This is an experiment which is actually trying to unravel the mysteries of the universe by trying to look at what happened at the time of start of the universe. Now, going back to this one, all ordinary matter consists of, as we know, atoms. And the atoms, they consist of protons, neutrons, along with a club of electrons here. But these protons and neutrons are not fundamental particles. They are also made up of particles, which are, for example, quarks and gluons. These quarks and gluons are truly fundamental particles, which were present at the very beginning of the universe. So what is happening is that the quantum physics today is engaged to study these tiniest or the smallest particles, which are the building blocks of the matter. And there is a hot pursuit in trying to understand how the universe was created, what happened, how the galaxies were formed, and also what were the conditions, what is going to happen to the universe, is it going to stay like this, or is it going to die out, things like all these questions. So we also know that the classical physics remained very powerful for a very long time, over a century. But with the middle of the 20th century, it was also understood that many things could not be explained by using the classical physics. And this we have heard in the last 2 or 3 lectures by Dr. Yesterday with Professor Ajay, and then also Professor Arvind day before yesterday. Now, the foremost information to unravel about the mystery of the universe is the mystery of the birth of the universe itself. And this is what scientists are trying to answer the question. Now, there are 2 classes, 2 different types of searches, 2 different types of ways of understanding this in terms of either the classical or in terms of the quantum physics. People or the scientists who are studying, they can roughly be divided into 2 or 3 categories. They are basically cosmologists, particle physicists, astronomers, astrophysicists, and some of them are freelancers or the sky gazers. Normally, how the mysteries are unraveled are by looking at some of the tools. The tools they engaged in trying to understand are either theoretical or experimental. By theoretical, we mean that we need to develop a theory, or we need to exercise or modify the current theories, which can predict a solution to find the mysteries of the universe. And secondly, the experimental part would be a solution which we find by utilizing this theory, and we obtain the results or the solutions through the experimental observations. These are the different ways. Now, on the theoretical boundaries, we have classical mechanics and we have quantum mechanics. But since we are talking of the particles, which are the tiniest possible particles, having almost virtually negligible masses, we talk in terms of the quantum-based theories. And these quantum-based theories, basically, they try to explore the origin of the matter, how the matter was built, how, starting with these tiniest particles, the whole universe could be built. And by considering these tiniest particles, if we try to look at how the matter was built, is there's some question? How the matter was built, we should be having a complete theory, which can actually go back, give us an idea how these tiniest particles build matter at a scale which is in large scale structures, which actually includes the formation of galaxies, which includes the formation of the stars and everything around us. So these theories are built, and the theories are built around the quantum mechanics. And we also understand that classical theories fail for certain phenomena dealing with these tiniest particles.
Please,
And
excuse me, please, all participants, please mute yourself. Please.
And
Sorry, ma'am.
And this is the way we go about. And the second aspect is looking at the experimental observation, making an experiment and trying to see whether what the theory is telling us is correct or not. But making an experiment in today's environment would definitely somehow we find a means of connecting it back. Theoretically, you can calculate. You can calculate the backward history of the universe. You can calculate the forward evolution of the universe. However, experimentally, what you observe today, how do you connect it to the backward and to the forward? That is the most important part, and that's the most difficult part here. There are several experiments going on in the world where people are trying to look for different mysteries, and these mysteries are connected not only with the origin of the universe, but also there are certain mysteries we are very much familiar now, that the whole universe currently it composes of only 5% of the visible matter, roughly 5% of the visible matter. We have almost 25% of the matter, which is called dark matter. And then you have 70% of the dark energy. All these are the mysteries which are unraveled, where only we can work with the quantum theories. Classical theories do not come to our aid. And in addition to this, there is another mystery which is regarding the particles neutrinos, neutrino oscillations, which can only be understood in terms of the quantum theories, not in terms of the classical theories. So it is a must that all these present day theories, knowing certain details of these mysteries, and we try to work out and try to connect to the origin of the universe, can be done only in terms of the quantum mechanics. So there is no other way we can go about it.
Oh, thanks, ma'am, for unfolding the mysteries of quantum mechanics. Now, my next question is to Professor P.K. Ahluwalia, sir. Sir, what is the quantum mechanics in a simple language, and what are its landmarks? Why this quantum mechanics is, surfacing in today's world, as a new concept, and why this classical mechanics is fading away. So, please, Professor Ahluwalia.
Yeah,
Professor
thank you
Ahluwalia.
very much. Yeah, thank you very much. I have understood the question. Look, it's like this, that at the end of 19th century, we were very much into classical mechanics. And there were certain areas of physics which were very well established. One of these was thermodynamics. Other was electromagnetism, or electricity and magnetism, or electrodynamics, whatever you want to give it as a name. Maxwell was the pioneer in that. And the classical mechanics was there since the time of Newton. And by the end of 19th century, we had reached a stage where we had started thinking that whatever we have to learn about the physical world, or you may call as nature, we have already learned it. We have a structure with the help of which, if any new problem will come, we will be able to solve it. It is a matter of, setting up a kind of a equation of motion or a differential equation. And if we have even very large number of particles in the system, at which we have to look at it. Maybe we will set up those differential equations separately for these particles, and people had started thinking that if we have enough computation power, maybe we will be able to solve everything. But nature always offers surprises. Sometimes we think that this is not possible, but that starts happening. In fact, one field of physics which really fascinated everybody, right from children to the researchers, that has been the field of spectroscopy. I hope everybody remembers the famous experiment of Newton, where he threw white light on a prism and it was split into 7 colors. Now, that was the beginning of, you can say, the spectroscopy. And during this time, chemists also were using spectroscopy to understand what is happening, say, in a molecule or in a particular atom, by doing very simple tricks like, they will take sodium chloride, take a Bunsen burner's flame, put sodium chloride in it, and the Bunsen burner's flame turns golden. And then they try to see what is this color, why this is actually coming. So this was the situation which was in the case of spectroscopy. And also, we had started realizing one fact, that matter is made up of atoms. Earlier, it was like some philosophical ideas which were put forward, say, by Kanad in India. The famous term Pramanu, which we call, actually came out from his vocabulary only. Then we had some other very interesting thoughts which were coming from Aristotle. There was some idea which was there. Dalton also came on the scene. So people were trying to understand that there is some constituent of matter which is elementary as far as matter is concerned. And chemists were, very cleverly able to find out what we used to call new and new elements in nature. And when one looked at these elements and their properties, Mendeleev was able to actually make a periodic table, which was a very interesting pattern, which happened just by looking at the properties of a class of elements itself. But it was very mysterious that why this pattern is there. This was a very big question mark. So this is one question which was a mysterious thing for chemists as well as physicists. But then the spectroscopists were working, and they were trying to create new experiments. New technologies were emerging, like a vacuum pump was there, a discharge tube came up. We had a way of converting low voltages into very high voltages, say 12 volt can be converted into 15,000 volts. And we had this very interesting device which we call as discharge tube. And with the help of this discharge tube, we started studying various things. Again, people saw spectra with the help of these discharge tubes. So spectrum was a very, very important signature which people were actually trying to study chemistry or elements or atoms or molecules, whatever you want to call them. There was a lot of confusion about this nomenclature also. So there was one other spectroscopy experiment which was based on the black body radiation. And this is a beautiful experiment in which you see a beautiful curve which you can draw for the intensity or the energy intensity, and what you say is along the x-axis, which you call as the wavelength. So this was done by very many people. And that was actually coming up as a kind of a puzzle, that how to explain it by means of, say, a single explanation. There were many explanations which were coming up, but there was no single explanation. So this was a very mysterious thing. And then at the end of the 19th century, this discharge tube also helped us to see what we call as the electron. The discovery of electron was very interesting. So now, at the end of 19th century, on one side, we were thinking that we know everything, but on the other side, we were finding that there are certain things which we are not able to explain within the realms of the classical mechanics. So this was what was happening. When the first decade of the 20th century came, Planck tried to look at this experimental result of black body radiation spectrum. And he also tried to apply his mind how to explain it. There were certain laws which were known, but he wanted to, bring them together to see whether I can have a single law to explain it or not. And he was able to succeed it. But for that success, he had to think of a fundamental constant which was needed to explain the whole curve. And that is, I think, the starting point of what we call the quantum mechanics. This is how quantum mechanics started. Even at that point of time, when he wrote his famous paper explaining the black body radiation spectrum, he himself was very skeptical about what is this H, the Planck's constant. And then we had discovered the electron. J.J. Thomson had found ratio of electron to mass. We also found that he gave us a model of the atom also. So now we had a model of atom, and we were trying to see whether we can also think of this kind of a model which can explain to us what goes inside the elements. Or can we really try to understand what is the reason that there is a kind of a pattern in the periodic table. Now, when we try to look at that era is actually called semi-classical era of quantum mechanics. And I think this era lasted right up to 1920 and 21. Now, if you look at modern textbooks of quantum mechanics, which we call as quantum mechanics only, what you will find is that these books didn't come out with a name of quantum mechanics. People tried to distinguish these developments from classical mechanics to what they started talking about as modern physics. So in this modern physics, there were many things which were, emerging. And one area which started taking shape as a result of this was what we call as quantum mechanics. In this next step was taken by Einstein in explaining photoelectric effect by means of a single equation, very well known to everybody. H nu is equal to H nu 0 plus half mv square. And he also introduced another idea of quantum, which was known as the quantum of energy called photon. And because, he had explained an experiment, it was a very fascinating explanation. But then people tried to look at what is the link between this Planck's constant, which Einstein was using now, inspired by what Planck had given, things started moving forward. And then we found that Rutherford's nuclear model came. We study these now in even class 12. After that, Bohr came on the scene and he tried to give a model which was very different from the Thomson's plum pudding model. And he tried to imagine that there is a nucleus around that electrons are distributed as if planets are going around the sun. So that is known as the planetary model. One of the success stories of this model was this, that when he wrote the postulates of this model, he also brought in this Planck's constant in quantization of what we call angular momentum. And he said that because there were certain objections which were raised on Rutherford's nuclear model that if there is an accelerating charged particle, it must lose energy and fall inside the nucleus. So that was a kind of an objection to nuclear Rutherford's model. Now here he said, no, electrons will not fall. They will be in specific orbits. And in these specific orbits, which he called as the stationary states, decision is taken by the fact that angular momentum is quantized. And with this, very easily, he could write down what is the explanation of the energy of the electrons in different orbits circulating around the nucleus. And that could explain beautifully, once again, a spectroscopic result, which was the spectrum of the hydrogen atom itself. And once people saw that it explains the hydrogen spectrum beautifully, it became a kind of a very interesting landmark for further probing the quantum world itself. In the meantime, there was another fellow who was looking at the electron. J.J. Thomson had given us the ratio of charge to mass, but he had not given us what is the value of the charge on the electron itself. So Millikan comes on the scene and he gives us what is the charge on the electron. But in doing that experiment, also, he was able to check what is the role of this Planck's constant. And fortunately, Millikan also measured for the first time experimentally the value of the Planck's constant, which matched with the value which was given by Planck and which was used by Einstein. So now we find that this part almost ended in the year 1920. In 1921-22, Einstein got a Nobel Prize for explanation of photoelectric effect. And then suddenly there were certain other things which started happening. People were not able to see that why Bohr's model fails beyond hydrogen atom, how we really overcome that. And they started searching for, once again, a fundamental equation of motion as good as, say, Newton's equation of motion. And that is where on the scene comes Schrödinger. And as yesterday's lecture explained it very nicely, that out of his grand intuition and by a kind of an axiomatic approach, he said, this is the kind of equation which is needed for quantum mechanics. And once we were able to see that equation, people started saying, you tell me the potential, and I will tell you how to solve this equation. So one of the first problems which was once again picked up by Schrödinger was the solution of the hydrogen atom Schrödinger equation. And it was very nicely, mathematically derived. We were able to bring the idea of quantum numbers beautifully in it. In the case of Bohr, there was only one quantum number, which was n, which was basically nothing but the principal quantum number. But here we were finding that we have principal quantum number, then we have this orbital angular momentum, then we have magnetic quantum number, and then by hand, later people put the spin also into this picture. And that actually brought in focus, what we call as the wave function. Now, everybody, when one wants to talk about quantum mechanics, one starts thinking about the Schrödinger equation, starts looking forward to the solution of a given Schrödinger equation for a given potential, depending upon the physical system which we want to study. And at that time, people started saying that any third-rate physicist can set up a Schrödinger equation and solve it and get first-rate results. And this is how, quantum mechanics began. And it was a great, great journey. But one thing I want to tell you, that success of quantum mechanics lies in the fact that it applies to the microscopic world. And most of the properties of matter which we want to look at can be understood by applying quantum mechanics to the microscopic world itself. Today, when we are talking of various technologies which have come up, you will always find electron is the hero of this movie of matter in nature. And we start playing with this hero and start explaining various things by keeping this electron into focus. For example, when we are talking recently, say, of quantum entanglement, one of the things which people are talking about is that, okay, I want to have a bit, but I want to have a quantum bit. How can I have a quantum bit? And they say, okay, why don't you take a cage, bring an electron there, and let it be isolated. You will find that this single electron in that cage will have two states. One is the up state and the down state decided by the spin of the electron. And now you have an entity which we call as the qubit. So when we are today talking about qubits, etc., I think ideas are being seen in the light of latest technologies which are available to us, which have let us go into these kinds of details. Also, if you look at any technology around, say your mobile, your television, the tools of information technology, you will find the hardware involves quantum mechanics in it. You cannot think of those things which we have been able to achieve without understanding this. But one of the first achievements which the Schrödinger equation was able to actually tell us was the complete explanation of the periodic table. Now, periodic table was no longer a mystery. We were knowing that how these electrons are distributed in an atom and how they are actually forming the pattern, which very intuitively and by studying the properties of the elements, Mendeleev was able to create. So I think I have answered your question which you asked me, that how quantum mechanics began and where it is. I think it's a very interesting story.
Yes, sir, very beautifully explained. Because rhythm is formed, just I want to ask one short question. Sir, classical mechanics, dominated by Newton in that era. How in quantum world should we give a father of quantum mechanics as Schrödinger or Planck's? Because in Planck's constant, as you said, that H is always sitting on every equation of a Schrödinger equation and so on. And who is going to play a dominating role? Is it Schrödinger or Planck's?
I think the credit must go to Planck.
Okay, sir.
And let me tell you a very interesting story also about it, that when Planck was looking at his calculations and he was trying to see that what should be there which is missing, he was able to do a bit of dimensional analysis there, and he found that there has to be something which should have the dimensions which are missing there. And he put in that constant there. And later we know that this is nothing but what we call as the Planck's constant only. So this is a very important part of it.
Right, sir.
Schrödinger was a great, what you call scientist in carrying forward and getting into the real nitty-gritty of the microscopic world. But the credit must go to the Planck.
Of course, sir. Now I move to Professor Madhurima. Ma'am, my question is how quantum physics can demystify quantum concepts and how it is, make more aware about the general public, how general public can perceive this quantum mechanics in a very simple way. And that's my question. Professor Madhurima.
First of all, let me congratulate the organizers on this very important event, and thank you for making me a part of this actually momentous program.
Thanks, ma'am.
How do we demystify quantum mechanics? To start with this, we need to understand what it is from a normal person's point of view.
Yes.
So I had no instruments to look at the universe and I was treating my body as a tool, what would be the minimum time that I could measure? It would be maybe the blink of an eye, a fraction of a second, and the maximum possibly the lifetime of a person. So which is about 8 orders of magnitude. Whereas the universe exists over 70 to 80 orders of magnitude over all dimensions, like, from Planck's time all the way to the lifetime of the universe. And this you can repeat for length, mass, whatever you do. So first thing we need to understand is that we as humans are very limited by our sensory perception of the universe around us. And that is what we actually call as classical physics, because that is what you can perceive, that's what you can see, and a lot of it is intuitive, so to say. Anything that goes beyond the human bodily sensory perceptions, it becomes a mystery because it's no longer intuitive, so to say. Can you translate something which is not perceived by these senses into something that you understand? If you were to translate a classic, either poetry or a good novel, you need to have a mastery over both the languages, the language in which the original was written, what was intended, and the language into which you're translating. So to demystify quantum similarly, you need to know what is happening actually in the quantum world. So you need to be an expert in that field and have the ability to speak it in the classical terminology. This comes with huge problems. The first problem is that there are no classical analogies to many quantum phenomena. Right. And not having analogies means that I cannot be translating something like Chandsa Chehra into a moon-like face. I mean, I don't have something to translate to start with. The second problem is the language itself. Because the language that is spoken in classical is understood by all of us because the dictionaries that we have created for human languages are to describe the phenomena that we see around us. They are not meant to describe quantum phenomena. For example, and of course, physicists have a very quirky sense of humor, and the way we use languages is also very funny because for angular momentum at a subatomic, subnuclear level, we have words like charm and flavor, which makes no real sense in translation. So what happens is a lot is lost in this translation because it goes from being science and physics to being metaphysics. And dangerously so, because people just try to look at the words and try to understand. So then comes the question, how do we really demystify it if this is the case? You will have to speak the language that is spoken in those regions, which is mathematics. So you need to have a deeper understanding of the mathematics, what it implies, and also the phenomena which are very different, because one of the bigger problems that exists while trying to understand quantum mechanics is a completely altered sense of reality. What is real? What is real in the quantum world is very different from how we define it in the classical world, because observables are very different. No experiment an experiment that's not performed has no result. And it's only on making a measurement that the experiment falls into one of its states, it collapses into one of its states. So there is a lot which has zero analogy in the classical world. So if anybody needs to demystify it, you need to find the right kind of a person who can understand both these languages, the quantum world and the classical world, and more importantly, understand the language that is spoken across all the 80 orders of magnitude, which is mathematics. So I would say that, understanding mathematical physics, which is a little different from understanding mathematics. Like, because when I look, when I look at an I in an equation, I understand it intuitively as a phase difference, not a square root of -1. The concept of a phase comes into my mind. That understanding is really required, and we need teachers and professionals who understand this to translate. Like I said, this is like translating a mega classic, like say the Mahabharata. This is not a task that can be taken up trivially. You need to really pay attention to it and then find the right kind of experts who can speak both the languages, because it is immensely complex. The altered sense of reality, if you understand it, is fairly simple because it speaks the language of maths and probability and everything else. If you don't, you can quickly go into pseudo-physics or metaphysics, and that's a very, very dangerous domain to be in.
Very right, ma'am. Actually, that was a really very eye-opener because mathematics and quantum mechanics should go hand in hand. They cannot be separated. So that's a wonderful answer, ma'am. And definitely at school level also. And if this quantum mechanics is being taught there or is going to be taught there, and they should have a strong foundation in mathematics. That is a must thing. So thanks, ma'am, for that view. My next question is to Professor Raman Johal. Sir, my question is, what is quantum computing? Today the world is always, having this charm word, quantum computers, quantum computing, quantum dots, and this era is witnessing this growth. And as Professor Ahluwalia said, that IBM has always, a front runner in doing this. When classical computers was there, and they were front runner in that era, and now quantum computers are there, and still they are leading the race. So, what is quantum computing, and what is its role in future? That's my question, Professor Raman Johal.
Okay. Yeah. Thank you, Sonic. You can hear me?
Yes, sir. Yes, sir.
Okay. Yeah. So first of all, I would like to thank the organizers for giving me opportunity to take part in this auspicious event. And I firmly believe that such events which are organized at the college level or even at the school level, they will really help the students and encourage them to take interest and be motivated to go into a research career. Okay, so congratulations a lot on this event. Now, coming to the topic of quantum mechanics, well, you have given it a very catchy name, Alice in Quantum Land. Although we don't find Alice in India, it's a name being given by Western scientists, or you can say Western community. Maybe in India, for Alice and Bob, we should find different names. But anyhow, yeah, so Alice and Bob, they play a very important role in this question about quantum computing. The computers around, they have revolutionized our way of working, way of thinking, and because technology always helps to minimize human effort, and it also speeds things up, right? So we are able to do a lot of things which were not possible to do by hand. In this context, you can talk about mathematical calculations, as Professor Ahluwalia said, that of the many systems of physical interest, very few are exactly solvable. So the solutions you see in the textbooks, like hydrogen atom problem, harmonic oscillator problem, and the simplest of them is the particle in a box problem. So they are exactly solvable, right? And that's why they are in the textbooks. But when you go to more than one electron systems, right, beyond the hydrogen atom, then you have to use approximation techniques. So there are techniques which gives you an approximate idea about the solutions, but then to go to multi-electron systems, you need a computer to do the calculation, right? So now we are interested in very large molecules, what orientations they take, what is the minimum energy of a protein molecule, and so on, how the molecules bind with each other. So all those things, they are very complex calculations. They do require computers, and that's why the computers have accelerated the pace of research. And we see that very rapid advances in science are made due to the computational facility. They are also helping in the symbolic computation also, not only in the numeric computation. But after all, the computers we have, they work on the principles of quantum mechanics. That is, for example, we have so many billions of transistors in a small chip. A transistor works on the principle of quantum mechanics, right? But still, the information which is stored in the computer, for example, in the hard drive of the computer, is in the form of the bits, right? it is in the form of the states 0 and 1. It's a binary unit of information, right? And then what the microprocessor or the information processor, it does is to make a very fast, large number of calculations at a very rapid speed, so that all the mathematical steps, they are done in a very small time, which a human being will take probably years, thousands of years, right? Now, the point is that when you talk about quantum computing, you are talking about an entirely different principle. Now you want to store information as a quantum mechanical state. Now, for those who have had a course in quantum mechanics, as many of the students must have, a quantum state can be in a superposition of different states, right? The most general state, if you have 0 and 1, you can have a linear combination of those two states, right? And that is the most general state. Now, this actually allows you to store a lot more information than the individual 0 and 1 states, right? And when you kind of allow this state to evolve in time, then this state can do computation at a much higher level. Higher level, I mean that it actually introduces what is known as quantum parallelism. It is like, yes, you are having many multiple processors which are working simultaneously to find the solution of your problem. So they are dividing the task and then they are working simultaneously. So that is the power of quantum computing, that if you encode the state or the information about the system as a quantum state, then it allows you to kind of make use or exploit the principles of quantum mechanics, such as superposition, entanglement of states, right? And then sometimes those tasks which cannot be done just by having a string of 0, 1, 0, 0, 1 bits, it can be done if you allow superposition or entanglement. Now, we have examples of very famous examples of algorithms like Shor algorithm, Grover's algorithm. For example, Shor algorithm, it is named after the person of Peter Shor, who proposed this algorithm, that you can factorize very large numbers in very small time. So, which was thought to be classically impossible or very difficult to achieve. For example, so many cryptographic kind of systems, no, banking and all that, they have this keys which are locked, which are based on this principle that in order to unlock that key, you have to factorize a very large number, and which is not possible even on a classical computer. On a quantum computer, it was shown by Shor that you can do it in a much faster time, right? And similarly, there are other algorithms also. So quantum computing basically operates on those principles, right? It is another thing that from a practical point of view, they have not been able to go beyond a few qubits, right? So if you really want to exploit their power, you want to scale up the computational power. That is, you want to have so many qubits which are working in sync, right? But to make a system where these qubits are stable and they keep their coherence, which is the superposition, which is allowed by the rules of quantum theory, if you want to make them stable, it's a difficult job. You have to do the things at low temperatures, and there are environmental factors which kind of destabilize those states, right? So from a practical point of view, it is very challenging, although all the big companies like Google and so on, IBM, they are making a great hype of it, as if the quantum computer on a practical level will be possible tomorrow. But to make it really viable, like we have the computers all around, to make it commercial, I think it will take some time. Yeah.
Thanks, sir. Thanks for your valuable feedback. Sir, very quick answer from you. The quantum algebra, is it something different from the, very difficult and different from the, that we study algebra? Is it complex?
Yes, yes.
quantum
No,
algebra?
no. It is basically an extension of Lie algebras. Lie algebras are there in quantum mechanics also, and they define certain symmetries in the systems, like the angular momentum algebra is SU2, for example. The quantum algebras, or they are also known as Q-deformed algebras. No, it's just basically a name for them. They have nothing intrinsically related to quantum mechanics as such. Okay.
Right.
So
Thank
yeah,
you.
that's a brief answer for that.
So over to Professor Manjit Kaur now. Ma'am, my next question is, ma'am, as Madhurima madam has just said that little knowledge is very dangerous, and she said that mathematics and quantum mechanics should go hand in hand. And if we confine ourselves only to language of quantum mechanics without mathematics, that will be pseudo, knowledge. So, ma'am, my question is, how can we inspire curiosity about quantum mechanics in younger generation, and how they will perceive this quantum mechanics, in that way?
So
Professor Manjit Kaur.
yeah,
Professor Manjit Kaur.
okay. So I will start with what Professor Madhurima said. I think she said very correctly, very rightly. If you do not know mathematics, it's very difficult to teach quantum mechanics. So therefore, I think uh, it's not everybody's cup of tea. Not everyone can be taught quantum mechanics. We have to look at the potential of the child, of the young mind, what the young mind wants to do. So making physics curriculum, which are more interesting and which are more captivating, starting early in the high schools, should be important. Secondly, we have to design the courses. They should be offered only to the students who are interested in science. It shouldn't be forced on. If they are not interested in science, they will not be able to learn good mathematics. If they cannot do mathematics, it will be all black and white for them. They cannot learn quantum mechanics. So I think we have to have very highly motivated teachers who can ignite these young minds, who can ignite the imagination, and the role of the teacher is very important. The classroom teaching should be more interactive. It should not be only a monologue. And we must have some sort of hands-on creative experiments. I mean, these days I know the way the mathematics is also taught in the schools is not really the way I understand should be. Many students, they just tend to go into cramming up the things, but an understanding at the root level, starting very early in the age, if you can clear their fundamentals, if they can learn these things very well, only then they'll be able to carry on. Only then we can imagine of producing a good stream of computer scientists who can do this, quantum physicists and so on. So I would say that Madhurima is very right, that we should not be trying to teach in a way which produces more pseudoscientists or then having a clear understanding of the thing. That's important. So our teaching at the school level must be good, very good. I think we should have the best teachers in the school. Once they
Thanks,
are
ma'am.
once they are very well trained, they'll be able to do it. It's only that when their foundation is laid, a strong foundation is laid, they'll be able to carry on themselves.
So nice of you, ma'am. Over to Professor Rajiv for next question. Professor Rajiv, can you hear me? Professor Rajiv?
Yes, I can hear you.
Great.
So, hello, sir. Good evening to everyone in the panel. So, my question is to Professor Ahluwalia. Why common man should know about the impact of the quantum physics in the last 100 years? So, sir, please.
Okay, thank you. Thank you very much, Rajiv ji.
Thank you.
I hope you are able to hear me. I think the discussion is moving in a very interesting direction. I remember one quotation from Carl Sagan, the great astrophysicist. And what he said was that we are using gadgets around us which make use of science and technology intensely, it will be very unfortunate if we do not understand what goes inside them. And it is very necessary that an effort should be made to make these understandable to the lay person also. And always efforts are made by different people in taking these concepts even to the lay person. I'll give you an example. George Gamow wrote a book, Tompkins in Wonderland, which was an effort to explain the theory of relativity to a lay person. If we imagine that the speed of light is, say, 40 kilometers per hour, then what are we going to see around us? So, some kind of picture is created in the mind of the reader that what is this after all actually happening? So this is very important to appreciate and understand. Now, we have already seen that in the last 100 years, I would say right up to middle of 80s decade, people had not started talking about this revolution of quantum computers till Feynman came on the scene and gave a set of lectures on theory of computation. It's a beautiful book, and I would request this audience to please read that book. And the beauty of Feynman, as is always there, which was also in his lectures in physics, is this, that he doesn't use very complex mathematics to explain how a quantum computer can be built. So he talks about qubits. He tells that how these qubits are different from classical bits, and how with the help of these qubits, we can make the basic building blocks of a quantum computer. So everybody who is sitting in this audience must be knowing that when we want to really make a computer, we always make use of what in electronics and in computer science we say logic circuits. We play a lot of games around these logic circuits only when they are introduced to the students. And they don't require much mathematics as we require, say, solving a Schrodinger equation itself. And once you know how to build those quantum logic gates, you are ready with a quantum computer. And he said, he predicted at that particular time that you will hear very soon, maybe in the next 20, 25 years, that the quantum computer will be there. So now if I start putting it like this, that the way we are carrying this mobile in our pocket, which is nothing but a typical classical computer, which is very powerful, if we are able to achieve the formation of those qubits at a temperature which we are able to, say, keep around the room temperature, we may not be very far from providing these quantum computers on the desktops or format. But even then, at the present time, the kind of progress which has been made in creating these kinds of qubits, which I gave you in my earlier introduction, that how a qubit can be formed in the form of a quantum dot where we trap an electron. Trapping this electron in a quantum dot requires that paraphernalia, which requires very, very low temperature. And what people today are doing, and they are trying to achieve that, is this: can we really try to bring these kinds of stable qubits at higher and higher temperatures? We are sitting in 2024. In 1924, quantum mechanics came, and in 100 years, we saw that how it has changed the world around us. I think in the next 25 years, the way things are progressing and the way things are being reported in the literature, we will be able to achieve that kind of a need. And also in his that famous book, Feynman talked about that whenever we talk of a classical computer, people talk about Moore's law, that how many, say, the components of a circuit can be put on a chip, how large that number can be. He said that in making of the quantum computers, you can go down to the scale of a molecule and see that there will be no such limitation which is there in the case of a classical computer. So I think things are very fascinating. And it is very essential that we try to talk to the young students, maybe starting from the school, to the undergraduate students, and to the PG students about it. I would like to tell you another very interesting aspect, particularly coming around quantum computing, quantum entanglement, quantum teleportation, etc., etc. And this is in the context of a very interesting dilemma which is there in the minds of teachers who are going to teach these subjects. There is a very interesting book which has been written by Mermin, that famous solid-state physicist who wrote a book on solid-state physics with Ashcroft. He has written a book on quantum computing where he actually brings out this dilemma very clearly. He says that this book, when I'm writing, I know that I'm not going to bring that kind of a rigor which is needed for doing quantum mechanics, but still, I can give that kind of a background to the students where without knowing that rigor, they can go ahead with the making of logic, quantum gates, etc., etc., and imagine that how a quantum computer can be assembled. And what are the basic things which he mentions one needs to know? He tells you need to know linear algebra, you need to know a bit of probability, and the rest of the thing you can go and learn as you try to understand basic concepts. And the fundamental basic concepts which are emphasized throughout in quantum mechanics, one of these is superposition principle, in which Professor Ramandeep also mentioned that if you have a system with, say, two states, by taking these two states, you can create, by superposition, a new state also, giving different weights to each of these states. And when you try to give different weights to these two states, you find that you can create a very large number of such new states. That is where a quantum computer is going to differ from a classical computer. So this is a very important distinction which needs to be made. And you know, IAPT is going to initiate a program very soon from 22nd April, which is focused on class 11, 12, and undergraduate students, giving them those fundamental ideas which can help them to see what goes on in quantum computing and how that can be understood and used also. You know, there is a lot of talk about quantum workforce which is needed in future. How can that quantum workforce can come? I think here is an opportunity that we encourage our students in the physics departments and who are interested in physics to get acquainted with this kind of a mathematics so that they can move in these kinds of fields. So there was one aspect that we should really let people know that what is going all around. We should also let people know that it is possible that you start early and master the things. This is what is the message I would like to give to this program. And in the end, I would also like to thank organizers that they have given me an opportunity to interact with a big audience, and hopefully they are enjoying this discussion. Thank you.
Thank you, sir. Thank you very much. So, sir, as I have also one, thing to add here. As you told that to bring a quantum device to a room temperature, so we need a great patience and very holistic approach over the time. So definitely with those two things, it will be at our room temperature. As sir, you might have come to know about the fudging of the data for superconductivity. Recently, a physical review letter has launched an investigation into the data where they claim that we have bring the superconductivity to room temperature. So definitely, sir, you are right.
I don't know actually what is the state of affairs. Yes,
need to
people
follow the
reported superconductivity
yes, sir,
data.
reported in March. In March, yes, sir, in March 2024, sir, they started investigation into this.
Yes, yes. So that was
Yes.
reported, and they said that they have got
Yes.
it. There was
Yes,
a lot
sir.
of confusion about it.
Confusion, yes.
I think for the time being, for the purpose of this panel discussion, I don't think that we need to go into that.
Yes, sir. Yes, sir.
These are the
Sure.
things which happen, and I think there are now systems in place to take care of all those things. So I don't think I have any comments to make on that. Thank you.
Okay. It's okay. Thank you, sir. So my next question is for Professor Madhurima. So, madam, are you there?
Yes, I'm here.
Okay. So, ma'am, what are the real world application of quantum mechanics?
Well, the entire universe in a nutshell. Because let's start with a simple question that my physics teacher used to ask us as an application for quantum mechanics. Rutherford's experiment, and we know that most of the atom is empty space. If that is the case, why is that we don't fall through the floor and all of us collapse into a single point? What's holding me on my first floor when I know that most of the space is empty? The answer to that lies in Pauli's exclusion principle. And the same thing when you extend into the universe, why is that stars don't collapse onto each other, galaxies don't collapse? And even when they do, like it happens in black holes, why is that information leaks out of it? So from one end of the spectrum to the other end of the spectrum, the entire universe is run through the ideas of quantum mechanics. So real world applications are practically everything. And take something as simple as, the color of a metal. A single atom does not have a color. Where does the color of a metal come from? Where does rigidity to molecules come from? The answer to all these questions lies in quantum mechanics. So that's basic physics. Talking about applications, I think one of the biggest contributions of quantum mechanics has been to material science, and the other has been to pharmacology. Material science being quantum modeling of bulk solids, and very broadly put, I'm overgeneralizing, and pharmacology being quantum mechanical studies of molecules. Since I work with molecules, let me take that example. So if I want to find a new drug, how does a person go about doing it? There was a time long, long ago, many centuries ago, where people would take, certain elements from around them, from nature, mix and match, give it to somebody, do a trial run, and ultimately figure out what works. As time progressed, we have had better ways of understanding. And with the advent of good computers, we have been able to replace lab rats with computations so that we have less damage on living beings. So when you do a quantum mechanical simulation, what you're trying to do is to find the best molecule that addresses the problem. And again, oversimplifying for this audience, one of the ways in which a drug works, we can understand how a molecule works, is the lock and key mechanism. Suppose you were to open the lock of your home at night when it's dark, and you have a bunch of keys. You find the key. You go on poking at the lock until your key fits in. And this is what molecules do within the body. So they try to fit themselves conformally, shape-wise, into the required position. And for this to happen, you need these interactions to happen about 10 power 10 to 10 power 15 times in a second. Otherwise, like I'm fond of saying, if a dinosaur were to take paracetamol for its headache, it would still be suffering from it. Because those are the time scales over which these bonds, if they're covalent bonds, they make and break. With the advent of computers, it's easy for us to understand the quantum mechanical nature of these bonds, especially the weaker bonds which actually drive life, which is like hydrogen bonds that are the dominant ones in biological systems. And by doing so, we are able to actually increase the quality of life of people. Right. So materials, practically every material from your everyday users to batteries, to green energy, to high energy materials, warfare materials, everything is today understood by going back to the fundamentals and looking at the quantum mechanical simulations of all of these. And the reason I'm saying simulations is because they actually help us to minimize the time and minimize the damage. We don't have to actually go and perform a hazardous experiment or test on living beings. We can do most of it in silico on computers. And so hence quantum applications are everywhere. Like I said, right from how the universe functions all the way down to how we function on an everyday basis.
So,
May
thank
I
you,
add
ma'am.
something to it, what ma'am said, ma'am Madhurima? There are very interesting things which are happening around us these days. And I'll give you some very interesting examples which are very fascinating. When we go at down to the nanometer scale, what we find is that there are certain properties which change at the quantum mechanical level of the system. Now, one of the best examples which I can give you is about quantum dots. Only last year, a Nobel Prize has been given on quantum dots, and they are very fascinating materials in the sense that if you take, say, gold and try to grind it in a mortar and pestle, you can reach a stage where the color of the gold will not remain golden. Rather, it will change. Now, this is precisely what was done by this team of scientists who got the Nobel Prize for quantum dots itself. And then, suddenly you find that somebody has done this. Did we find some use of it, or it was just to put it in a bottle and tell, look, gold is not looking golden, but it is looking pink or magenta, or its color is changing. You can create full spectrum by changing the size of the system itself. So what we are doing is, as I was saying, we have confined an electron in this quantum dot, and we have created what we call as an artificial atom. Imagine now, this is what people are doing. And once we have these, people started thinking, can I have a technical application of these? And answer to that comes yes. Today, if I go in the market, I can have a computer, a television, which has what you call screens, which are quantum dot lit screens. And what they have done is they have shown that the optical properties of these are such that you can create the red and green colors, and you can have a background blue panel with the help of which your screen becomes so bright and beautiful, which was not possible earlier. And we have brought a new concept also in it, that is of an artificial atom. Look, when quantum mechanics came, people started talking about radioactivity. People started talking about what we call as artificial transmutation. Now, when we have reached the 20th century and at the end of it, we were finding that we have quantum dots. And suddenly we are finding that there is a technology which is available, which is being used around us in day-to-day usage. And the best part of it is that if you go back to the quantum mechanics class, you can study this quantum mechanics very easily without the complexities of mathematics. very intuitively you can solve a Schrödinger equation for a what you call three-dimensional quantum dot, and try to play with its size to see that how energy levels get changed. So now what you are saying is that you are also, not only creating artificial atoms, but you are able to tailor their properties also by changing their size. So the technology is playing at that level. And this quantum dot is also turning out to be the basic element to play with in the formation of qubits, as I mentioned earlier. So I think it is a very interesting, fascinating area. But fundamentals of quantum mechanics are required. More you understand those, better you will be placed in the race to achieve, greater understanding of the things around you. I'm saying things around you specifically, because you are now surrounded by all the way quantum devices. Don't forget that. When I'm holding this mobile in my hand, that actually is nothing but a kind of a quantum device. So thank you very much for giving me a bit of a time. Thank you.
Thank you, Professor Ahluwalia, for throwing the light on the application of quantum physics. So if we be, sir, I just want to add here one thing, that if we go back to 1920s, so people from other streams of physics have a very strong objection to this particular area of the physics. What is its uses, why so, and really we need to have such a physics which is based on totally probability. And but the ripening of such a concept of physics took almost 100 years to reach this level. So really you are right, sir, it's not a, I mean, McDonald's burger. It took time, and we need to keep a pace with the basic concepts always. Thank you, sir. And next question to Professor Johal. Sir, can you please throw some light on quantum entanglement in our everyday life? For a simple layman, what is quantum entanglement?
Yeah, okay. So I've been looking in the chat also about some students' questions. So I thought probably we should also attend to them. And I gather that we are talking about quantum mechanics, and as Professor Ahluwalia pointed out, that it is very important to learn the mathematics of it, and then only you can hope to apply it to some physical problems. But students often complain, and also it is the kind of purpose of this meeting also to demystify the quantum mechanics or its concepts for students. So that's not an easy task, and if I may quote Richard Feynman, he said that nobody in the world can claim to understand quantum theory, right? So we only know how it works, right? And that too through mathematics. But if you want to have a picture, intuitive picture of it, of the phenomena at the atomic level, we don't have that picture, right? So that, I think, is in the nature of the formalism or the theory. And some people do feel that it is not the final theory we have, that quantum mechanics has to be superseded by something, a larger theory. And of course, people are trying to kind of merge together different theories, for example, quantum theory and gravity, to create a quantum theory of gravity, and they have not been very successful at that. And also, even Madam Manjit Kaur, she talked about the understanding of the subatomic particles, that going beyond the standard model and to include other things also is not very trivial. So for the students, my advice is that while being students, you try to learn the framework of this theory, and don't bother too much about getting an intuitive picture of it, right? Nobody has been fully successful in getting that picture. So you are not alone in that. Even Feynman said that. And so if you learn during this time, as they say, you are able to sharpen your tools. Then probably at a later stage, if you are still in research, you can attend to the more conceptual problems which attend to this theory. And there are very basic fundamental questions about the nature of the theory and its interpretation, which have been around with us for over 100 years, and they have not been fully solved. Although we have made very rapid advances in technology, and we are at the threshold of quantum computers and so on. But still, at the conceptual levels, there are so many questions in the foundations of quantum physics that if a student is not, as one student has pointed out, that he or she is not interested so much in computation, but in the physics and mathematics of it. So I would like to say that there are problems which don't require much computation, but still you can do your job if you have the basic mathematical facility. Okay, so now coming back to the question about quantum entanglement. Quantum entanglement is actually at the heart of quantum mechanics, if I can put it like that. So sometimes people say that quantum superposition is very quantum in nature, but that is not true. Once you agree to treat the particles, so-called electrons, as waves, then waves can superpose, right? So they are the solutions of Schrodinger equation. So it's a linear equation. If there are two solutions to the equation, then their superposition or the linear combination is also an allowed solution, right? But entanglement, on the other hand, which applies usually to a bipartite or to a multipartite, a system which has two or more than two number of particles, is actually an existence of correlations, which are correlations that one part of the system has information about the other part, and globally the total system has some additional information which the local parts do not have. So it's a very non-intuitive idea, which is called quantum entanglement. And actually, there's a very interesting piece of history about this also. This term was probably coined by Schrodinger himself in 1935. But then the idea originally came from Einstein and some other co-workers. Einstein, as you might know, he was very uncomfortable with quantum theory. So although he helped a lot, actually incited the initial development in the hypothesis of the photon and so on, but he was not very ready to accept the implications which become obvious by Heisenberg's uncertainty principle, or even with the Schrodinger's wave function interpretation. But so to counter some of his objections about the quantum theory, Einstein had this thought experiment in which he took two particles, like maybe one particle of the, say, zero spin. It decays into two more fundamental particles, and they fly apart from each other, away from each other, to conserve the linear momentum. And then now the state of these two particles is not independent of each other. It is correlated, and in technical terms, it is called the entangled state. You can also say that a state is entangled if you cannot write it as a product, in a factorized form, as a product of the states of two local subsystems. There are some extra correlations which are not there in the local states. So Einstein gave this thought experiment, and his conclusion was that because of the existence of these correlations, which can actually travel faster than speed of light, which is forbidden by the relativity theory, he said that the quantum theory is actually showing you an example in which it cannot explain the results of this experiment. So he concluded that quantum theory is actually incomplete. So that was his conclusion about that. But it brought to attention the concept of entanglement between quantum particles, which was not appreciated earlier. So this idea was there for, say, last 80 years. But then recently, or not so recently, the 60s or 70s, John Bell, he reformulated this thing, and then he actually came up with an interpretation of, you can say, quantum theory, in which he said that if, as per Einstein, we try to complete this theory, Einstein said the theory is incomplete. So he said there are some hidden variables. And if you, with those hidden variables, you try to complete this theory, then can you get the predictions of quantum mechanics from that theory? And his answer was actually, it's not so simple, so easy to put those things into words, but this is one of the landmark results in the foundations of quantum theory, which came in the form of Bell inequalities. So Bell theorem or Bell inequalities, it actually forbids you to make local realist theories about the quantum phenomena. So quantum mechanics is inherently non-local, by which I mean that the correlations, they can be non-local, they can be not local in a sense. And the other thing is that you can't have the pre-assigned properties to the particles. Okay, so again, this has to do with the interpretation. When you think about these properties of the quantum particles, say, you don't find any analogs in the classical theory. In the classical physics, we say that a particle has a certain position, certain momentum, and those properties, we think that they can be assigned to that particle. But somehow it seems that in the quantum world, those properties, you can't interpret as if they were pre-existing. No? That creates contradictions in the conclusions of the theory. So quantum mechanics has many mysteries which cannot be resolved really at the undergraduate or the graduate level. So those things are there to be explored in your later parts of the career. But for the moment, it is only advisable that you learn the tools or the tricks of the trade, how it works. If you learn those kind of techniques, mathematical techniques and the computational ones, then you will be able to simulate the quantum systems and then able to predict the properties. And as the evidence is there, we have been able to create technology based on those same equations, which we do not physically understand in complete depth. And then based on that, we are able to make predictions also. And no prediction of quantum theory has been found to contradict the physical reality. That is a matter of fact. And that's why quantum mechanics has stayed. And whether it can be completed or superseded by another theory, that remains to be seen. And the people have not been successful fully to make a kind of more complete theory, as I said. So quantum entanglement is very important for quantum computation. There are many tasks which cannot be done if the states are not entangled. If you have what is called a quantum resource, additional resource of entanglement, then you can think of doing some tasks which are not possible without that. So entanglement gives you that practical advantage. And now initially they were able to make entangled states by various means. But now they are able to generate entanglement at a very large distances also. That is, two particles which are separated by, say, 100 of kilometers, but still they show correlations between each other, although there is no physical thing which is connecting them, so to say. Yeah, this is what I want to say.
Thank you, Professor Johal. Thank you very much for explaining quantum entanglement in very simple words to the audiences. So now I request Dr. Sonik, please have a next round of the discussion.
Professor Ahluwalia, shall we go to the chat box and answer a few questions? And if you allow us to do that, Professor Ahluwalia, or should we go for another round?
Yes, we can go to the chat box because I think this is okay. We have
yes,
essentially covered almost everything.
Yes, very, very deep. Professor Raji, can you ask one or two questions from the chat box?
Okay.
Professor Ji,
Yes, yes.
only 1 or 2 questions.
Yeah, sure. So, sir, there is I'm not able to, recall the name of the candidates, but there is a question that, so it is an open question to all the members in the panel. Does the theory of quantum entanglement in computational means they contribute very greatly to the quantum information, in fact, and help us to achieving the travel of data by breaking the velocity of light? And next question is please explain. Question is, please explain symmetry, role of symmetries in quantum mechanics.
Actually, we can take these things. Professor Ramandeep, would you like to really comment on this question of quantum entanglement, which is there?
Yeah, I also read that question. So probably the student wants to ask that whether you can, as I mentioned, that if you have two particles which are separated from each other, and we make a measurement on one particle, right? And then the entanglement says that you can tell something about the state of the other particle, which may be thousands of kilometers or even at another galaxy, if the initial state was entangled. Now, the thing is that initially it was thought that the information, when you make a measurement, now we also know that when in a quantum system, the state is not pre-existing. So when you make a measurement regarding, say, you want to measure whether the spin is up or down, right? And you get the result up. Now you can immediately say that if you measure on the other system, it will be down because your initial total spin was 0. So the thing is that the axis around which you are making a measurement is entirely up to you. So how does the information travel from one part of the system to the other spin, right? Which may be very far off, as I said. The thing is that although it seems that some influence has traveled from one part of the system to the other, it cannot be used to kind of send information. So the rate at which information can be sent, the maximal speed is the speed of light. Right. So the short answer is that entanglement or entangled states do not violate the principle of relativity. They respect the relativistic principle that information can be sent at the maximum speed, which is that of light.
So I think this question gets answered. You have commented on the idea of luminal velocity very nicely. Now, there are certain things regarding symmetry.
Yes, sir.
On the, for example, in quantum physics, BRST symmetry was first discovered as yet another symmetry of gauge fixed actions. We are interested of the ghost fuel. The ghost field plays a more important role. Why? Look, I am sure that I don't know the answer to this question because I don't have any knowledge about it. If any panelist knows about it, please comment on that. If not, I think there are certain questions which should remain unanswered. That is what will help us to go ahead also.
There is another question. A role of symmetries in quantum physics.
It is at the end of it. Yeah, actually, I think symmetries play a great role in physics itself. And one talks about these symmetries a lot in particle physics. Maybe Ma'am Manjit can really throw a light on that. Parity is one. Gauge symmetries are there. And there are lots of other things which definitely play a role because symmetries actually tell us
Yes.
what are the distribution laws which emerge out of them. And they are very interesting. At the moment, I can make that kind of a comment only.
Yes, sir. Thank you, sir.
There
Yes,
is another question which has been posted. Ma'am, Manjit, would you like to comment on it?
Yes, as you rightly said, that symmetries play a very important role in particle physics, and I can actually quote one of the examples, where there's symmetry breaking in the electroweak field. If the students are already familiar with it, that actually leads back to the generation of the Higgs field. And Higgs discovery has just been a few years back, a decade back has been done. And that was a wonderful example of symmetry breaking mechanisms. But they are a little more complex, I would say, at the moment to explain in terms of simple words. But I would say, yes, whenever there is a breaking of symmetry, the nature is symmetric, and we expect the phenomena to be symmetric. A very simple case is that when the universe was born, the matter was produced in the form of hot soup, like it was a quark gluon soup. It was expected that the matter and antimatter would be created in equal amounts. Now there is a symmetry breaking here. Now in today's world, we see only the matter, and the antimatter is completely missing. And what has happened to this antimatter? Where has it disappeared? It is again a mystery, another mystery of the world. Now there are a lot of theories which are coming up that it's simple, if there is a sphere, if you break it up into two halves, you get one hemisphere, you get another hemisphere. It's like that. And so yes, if there is a little imbalance, for example, now people are saying, some theories say that even if there was one atom more for the matter would stay on and the antimatter would disappear. So in this sense, I think there is a lot to read about it. There are a lot of symmetries one can actually think of. These are not particularly for the quantum mechanics, but I think quantum mechanics lies at the core of almost every theory, basically, which actually runs the universe, which actually is at the heart of the things around us. Maybe Dr. Ramandeep can put some more light on it.
No, ma'am, actually, you put it very nicely. Yeah, so the symmetries, as Professor Ahluwalia also emphasized, that symmetries play a very important role, in the whole of physics. So, in classical mechanics also, we talk about spherical symmetry, which leads to conservation of angular momentum, right? And then he talked about parity. So based on our expectations that nature would be symmetric, you expect that in the beta decay also the parity will be respected. But it was a huge surprise when we found through experiment that there's a violation of parity. And so this Higgs mechanism also, which is called spontaneous symmetry breaking, which leads to the masses of the particles, is also another kind of symmetry breaking, which so the matter-antimatter symmetry is also there. But at the level of kind of elementary quantum mechanics also, so symmetry intrinsically implies the invariance in the system, right? So if you have a spherically symmetric system, you rotate it in 3 dimensions, it will remain the same, right? That is what we expect. So there's a very famous theorem, mathematical theorem, which was found by a woman mathematician at the start of the 20th century, which is called Emmy-Noether's theorem, which relates symmetries to conservation laws. So every conservation law is a consequence of some kind of symmetry. So you have energy conservation and conservation of linear momentum, even in quantum mechanics and also in classical mechanics. So the underlying reason for that is you can ascribe some kind of symmetry to that. Apart from that, there are dynamical symmetries, which are still higher levels. So you have some algebraic structure associated with them. And they are not just the space-time kind of symmetries, probably. Yeah.
And
There's another thing also, in superconductivity, for example, people talked about spontaneous symmetry breaking. And that idea, in fact, led to a lot of thinking among particle phases that what must be going at the back of it. So these are the places where such things happen. Phases become alert to see that what is going on here. Yeah, ma'am, Madhurima, you were saying something, please.
yeah, I was saying that at a slightly more fundamental level, even the choice of the basis set when we solve problems like the hydrogen atom depends on the symmetry that is there, because the special functions that we choose as basis sets do depend on the symmetries that are inherently there. So yeah, they play a role at every point.
So I think, Sonikji, we are
Thanks to all panelists. Actually, this ocean of quantum world is very deep, unending. So we can't more dig out of this. More we get deep inside. So that's an unending world. So Professor Ahluwalia, I must congratulate you that it was very successful event, and I must congratulate to Dr. Neetu Verma, our head of the department physics, who put a lot of hard work with her team, and of course followed the footprints of Professor Walia, who just instructed and guided us from time to time. So thanks a lot, Professor Madhurima, Professor Johal, Professor Manjit, and of course our leader, Professor Ahluwalia. So, Madam Neetu, if you want to say something.
It's exactly right. Very thanks to all our panelists and very energetic moderators too for making this panel discussion a wonderful discussion. So it's from core of my heart, I am thanking all of you for sharing your insightful perspectives on quantum mechanics. Really, your thoughtful analysis of quantum phenomena has deepened our curiosity for the topic that is the mystery of the quantum world. So I am really thankful to all of you, especially to the panelists and the moderators, Dr. Sonik and Dr. Rajiv. So hope to meet you in future next day. Thank you, Anand, for making each and every part to be very successful under your guidance.
On a last lighter note, Professor Ahluwalia, I just would like to hear, classical music is very difficult, and Sugam Sangeet is very easy, light music. And in this case, classical mechanics is easy, and quantum world is, they are complementary. So put, throw light on this.
When we learn these things, they both are very difficult. Let me tell you, physics is a very hard taskmaster. It's not easy, and everything which we learn gives us a new level of achievement also. I would like to put it like that for young students. And, as I always try to tell my friends and students, learning physics always means that you are in the company of great minds. And today we were in the company of great colleagues here who really let us work on this subject which we had chosen for this panel discussion. It's very difficult to know everything we know, but I think you made it a grand success. And please don't treat classical physics or quantum physics as Sugam Sangeet. Both have their own intricacies. So on that note, I would congratulate the organizers of this program that you have done a great service to IAPT. I am looking forward to tomorrow's lecture also, which is going to be very exciting by Professor Deshmukh. I would like to invite each one of you to that lecture. You will hear a man who knows things in detail, and he has written a book on quantum mechanics, which is very modern book, I would say. So we are looking forward to that tomorrow's session also. Thank you very much. As president, I must thank from the core of my heart that when IAPT thought of doing it, Kanya Maha Vidyalaya and the physics team there came forward that we will do it. And I think you have made it a success. Thank you.
Thank you,
Thank
sir.
you.
Thank you. Thank you very much.
So I think we can now
Thank you, sir.
log out. Thank you.
Thank you. Thank you, Manjit ma'am, Madhurima ma'am, Johal sir.
Thank you
Thanks
very much.
a lot for making this
Thank you.
event a successful. Hope to meet you in future too. Thank you. Let's close this meeting.